Hi everyone. Today we are going to go over section 3 of chapter 2. And it's going to involve chemical bonding and different interactions between all of our elements. So last time we talked about our valence shell of electrons, and that was our outer shell. And if you remember, group 1 had 1 valence electron, group 2 had 2, group 3 had 3, and they just kept going on like that all the way up to group 8 that had 8 valence electrons. And this is what we're going to be worried about today when it comes to chemical bonding. So we're going to first go over covalent bonds. Now, there's going to be 2 main bonds that are fairly strong. They're covalent bonds and they're ionic bonds. Covalent bonds are going to be ones that they're going to share those valence electrons. So no one's going to gain or lose electrons. Instead, they're just going to be sharing them between the two. And again, this is all going to be with respect to the valence electrons only. Once these two bond together, we are going to get a molecule out of it. It's unlike ionic bonds. Ionic bonds, they share, they gain or lose electrons, and they make compounds. So here is an image from your book that goes over the bonding between 2 hydrogen atoms. And that one's pretty simple. I can show you guys that one, but I'd rather show you something a little more complex that goes with oxygen and nitrogen. So we're going to do some bonding in between them. And if you look here, it says hydrogen bonding to hydrogen right here forms a single bond. I'll be able to represent to you guys what that means and show you the difference between that and our double oxygen molecule. So let me draw some things for you. I'll do the best of my ability. Instead of starting with hydrogen, let's start with lithium. Why? I don't know. I just feel like starting with lithium. If we have lithium here, Li, okay, we can draw it where we have all those different energy shells and all this stuff, and I just don't feel like drawing it like that. So instead of doing it our traditional way with all the different energy shells, let's draw it different. And this is called a Lewis dot structure. And for a Lewis dot structure, guys, you no longer have to worry about drawing all those energy shells, because all we're worried about in the Lewis structure is going to be our valence shell. So what we're going to do is we're just going to come around lithium and put 1 electron there. And lithium is in group 1, so it has 1 valence electron, so we're done drawing lithium. Okay. If I wanted to draw calcium in group 2, calcium, it's going to be Ca, and calcium is going to have 2 valence electrons. So our order of doing it is we're going to put 1 on top, and then we're going to put 1 on the side. So it's pretty much like we have 4 areas, guys. We can go top, right, bottom, or left. What you have to do is you have to put 1 electron on each side and then start doubling up. So on the periodic table, let me skip ahead because I think you guys kind of get what's going on here. I'm going to skip ahead all the way to nitrogen. And nitrogen, its Lewis dot structure, symbol is N. We are going to have to put 5 electrons around nitrogen. So to do this, we're going to put 1 on top, 1 on the right, 1 on the bottom, 1 on the left, so now we have 4, and then I'm going to come back up and I'm going to double up. All right. Now here's what we need to know for these areas. If it has 0 or 2 electrons in any area, it's not going to bond. So no bond in that area. Okay. So what I'm talking about for the 0 guys is in lithium, this area here, this area here, and this area here. All 3 of those are not going to bond. 0 in calcium, down here, down here. The 2, right here in nitrogen, so that's not going to bond, okay? But in nitrogen, we have these 3 areas here where it only has 1 electron in any area. So 1 electron equals a bond, okay? And it doesn't matter where you put these, as long as the diagram looks like this, guys. We can also make nitrogen look a little bit different. Here's our N. We can put that non-bonding area anywhere we want. It doesn't matter. As long as we have 3 bonding areas and 1 non-bonding, it doesn't matter the actual sequence you do it. Okay. So let me get rid of this and let's do some actual bonding here. For oxygen, now we'll start with hydrogen. Okay. Hydrogen has 1 valence electron and that's it. Okay. And we're going to bond it with another hydrogen that also has 1 valence electron. Okay. So we have 1 bonding area here and here in each of these. So when we form a molecule with our hydrogen, I'm going to move these around a little bit. Okay. You know what? Let me make this a different color here, guys. There we go. Okay. So if I make this H, we'll make it in red so you guys can see what's going on with the electrons. Okay. Let me erase this guy as well. There we go. Okay. So I'm going to redraw this first hydrogen, but instead of putting the electron on the top, I'm going to put it on the side, and you'll see why in a second. Now my second hydrogen, I'm going to draw right next to it. And here is its shared electron right here. So they're sharing the electrons in the middle. And what this means, guys, if I want to get real messy here, this red electron here, okay, watch carefully because this is going to get really clustered very quickly. This red electron is going to go around hydrogen, and then it's going to go around the other hydrogen. And it's going to keep going back and forth and back and forth and back and forth. So that electron is shared. Even though it's the red electron we're talking about with the red hydrogen, it's going to keep going back and forth between the red one and the black one. Okay, so that is our hydrogen. Now, if we were to draw this a little differently, once again, okay, I'm not going to worry about doing the colors this time, but when we have 1 pair of electrons shared, we call that a single bond. So what we can do is we can just make it like this, and that little line in the middle represents right there, that is a single bond. Okay, so there's a single bond. Let's do an oxygen bonded with a oxygen. Let me change my colors up here so we can differentiate between things. So oxygen bonded with an oxygen. So let's start with the black one, and it's going to have, if you look at your periodic tables, it's going to have 6 valence electrons. So 1, 2, 3, 4, 5, and 6. Same thing with the other one over here. 1, 2, 3, 4, 5, and 6. So we have 2 areas that are non-bonding. On both of them I have them represented on the top and the right. And then we have 2 areas that are bonding. So here's what we're going to do. Let's make a single bond first. So we'll come over here and we'll make our single bond. Start off with the black oxygen. And I'm going to move things around a little bit. So I'm going to put the single electron here. Keep our double ones here. I'll just throw a single one there. Okay. So we have here a bonding area, and down at the bottom a bonding area. Okay. Let's connect our green one here. So there's that. And I'm going to draw it so it looks almost like a mirror image of the other one. Okay. Now, we're good here. We have a single bond in the middle, just like we had on hydrogen. But here's the problem. we still have a bonding area on the bottom here, which isn't good. We do not want to have an extra bonding area somewhere because we can have other elements come and bond to it. Now this oxygen right here, guys, O2, we have two oxygens there. This is the oxygen we breathe, so we definitely need it to just be O2. We don't want other elements to come and bond to it. So what we're going to do is we are going to take them and we're going to put them into the middle. Okay? So let me redraw everything. We are now going to have our oxygen. We're going to have the two on top. We're going to have the two on the side. And I'm going to draw it like that. You guys will see what I'm doing here in a second. Let's draw my other oxygen. Two on the top. Two on the side. And there we go in the middle. Now everything is bonded, guys, and we don't have any more bonding areas. So if we wanted to draw this a little bit cleaner, which I'm not going to worry about colors now, we're going to have our oxygen on the left. We are going to have a double bond in the middle. And then our oxygen on the right. Okay? So because it has two bonding areas here, that is why we need to share two pairs of electrons. And that's why we're going to have the double bond overall. Okay? Let's do one more. So this time I'm going to clear this board just so I have a little more space. So single bond up top, double bond down at the bottom. Now we are going to do nitrogen. So 1, 2, 3, 4, 5 valence electrons. And we're going to add it to another nitrogen. Just make it a different color. 1, 2, 3, 4, 5. And I think you guys can already probably see what's going to happen because we have our non-bonding area at the top and then the other three are all bonding areas. So let's start pulling things toward the middle. Okay. So what I'm going to do, keep our non-bonding region on top. We got that guy there. And let's start sharing some things. Here's our other nitrogen. Okay. So we have these two which would share together, guys. But what I'm going to do, whoops, I forgot one on the previous nitrogen here. What I'm going to do is I'm going to start just bringing it to the middle. So let's bring these two to the middle, this guy and this guy. And then we can bring the other two, this guy and this guy, to the middle. So overall, we're probably going to have, what, 1, 2, 3, 4, 5, 6 electrons in the middle. And this is going to look a little weird until I draw the blue one in, but go here, here, go here. Let's draw our blue one in. And you guys can see we have 6 shared electrons in the middle. No more bonding areas out here. But 6 electrons is 3 pairs, so that's going to be a, if we redraw this correctly, a triple bond. Okay. Now what do you guys need to know about the bonds? Well, the single bond, we're sharing 1 pair. The double bond, we're sharing 2 pairs. The triple bond, we're sharing 3 pairs. Which one do you think is the strongest? Well, if it's triple, it's going to be the strongest. So the triple bond is stronger than the double bond, and the double bond is stronger than the single bond. Okay? All right. And here is some of the stuff we just drew, guys. Here's one with methane, okay, down at the bottom. Now, the carbon on that was in that weird area with 4 valence electrons. So we said that yesterday that carbon isn't going to want to gain 4 and it's not going to want to lose 4, that row in the periodic table, that group, is not going to gain or lose. Instead, it's always going to share its electrons. So that group, guys, that group 4 that has 4 valence, what it's going to do is it's always going to do covalent bonding. It's not going to be doing any ionic bonding because it doesn't want to gain or lose, because it's like at a stalemate with the 4 and 4. It could lose 4 or gain 4. So instead it's always going to share. That way it's not worrying about gaining or losing. Okay. So we kind of already went over this, guys. Just talking about the valence, talking about the number of electrons and how it influences the number of bonds it can form. Okay. And then we already did this, but we're going to talk about water a little bit. And here is the non-Lewis structure, the Bohr model of water. And you guys can see that water has, or I'm sorry, oxygen has 1, 2, 3, 4, 5, 6 valence electrons. And if you look at the periodic table, you'll find that as well. Those 6 electrons in its outer shell will allow it to bond to 2 atoms of hydrogen, and that's how we get water, okay? And here's that picture of methane, guys. Methane, 4 valence electrons. It can make 4 bonds, so it can bond with 4 different hydrogens. Now, electronegativity, guys, is the atom's attraction for the electrons in a covalent bond, okay? I'm going to do an example with water on this, and there's a big, we're not going to worry about this too much, but there's a big chart in chemistry that has all the electronegativities of every atom, and we're not going to worry about all that. So the more electronegative atom is going to pull the electron toward it most of the time, okay, or more often. So here is our chart, guys. Our periodic table. Now, the electronegativity chart has a bunch of little numbers on here, which again, we're not going to worry about. But atoms that, if they're bonding together, if their electronegativities are very close, they're going to share that electron equally. If their electronegativity numbers are further away from one another, they're not going to share it equally. And the one that is a higher number is going to have it more often. So there's only 2 examples we're going to go over with this. And oops. Those 2 examples are going to be the methane example, which is carbon bonded to 4 hydrogens, and then we're going to go over the water one. So a nonpolar covalent bond, this is a bond whenever the atoms are shared equally. Okay, I'm sorry. Yeah, equally. A polar covalent bond is when they are not shared equally. So in a polar covalent bond, guys, one element is going to have that shared electron more often than the other, okay? And we're going to talk about partial positive and partial negative whenever I do the diagram. So here's a water molecule, okay? I'm not going to worry about this right now, guys. I'm going to draw it out, and I think it'll make a lot more sense for you. So let's draw water just as we know it. And I'm going to do the big model here, guys. I'm going to do the Bohr model. So we're going to have our nucleus of oxygen. Okay? So we're going to have in oxygen 8 protons, and we're also going to have 8 neutrons. Okay? And then we're going to have our first shell that we're going to fit 2 electrons in. And then our second shell, which we are going to fit 6 electrons in. 1, 2, 3, 4, 5, and 6. Okay? So there's our oxygen and water. Okay, that guy's oxygen. What I'm going to do here is I'm going to attach our hydrogens. I'm not going to worry. I'm going to draw the nucleus really small, guys. I'm not going to worry about putting the protons and the neutrons in, okay? But let me draw my hydrogens up here, okay? There's 1. And there's our second one. And here's our nucleus in the middle, And then here is our electron. Let me draw this nucleus a little bigger so you guys don't think it's an electron there. There we go. Okay. So here is our bond. We got two bonds. We have one here, and then we have one over here. So what's going to happen here, guys, is you already know that this is where we have a covalent bond. But we don't know right now if it's a polar covalent, which is shared unequally, or a nonpolar covalent, which is shared equally. So let me show you what happens here. With water, okay, this is the one example you got to remember for this type of covalent bond. Again, it's water. All right. So with water, guys, these electrons are not going to be shared equally, okay? I'm going to make this red one green. We're going to highlight it, and I'm going to show you what happens to that green electron. And again, that green electron belongs to hydrogen. Okay? Oxygen has a much larger electronegativity compared to hydrogen. So let's trace the path of this electron. What's going to happen is it's going to go around our electron cloud and hydrogen, and then oxygen is just going to say, hey, we're sharing, right? And then the electron, yeah, it goes around the outer shell of oxygen. And oxygen's like, oh, I like this electron. And what happens, guys, is it just keeps going around oxygen. And it keeps going around and around and around and around and around and around and around. Okay, Colm, you know that's enough. All right. So what happens is it's going to go around oxygen like 1,000 times. And then hydrogen's over here like, dude, we're sharing. Share. And oxygen's like, okay. So hydrogen will get it, maybe for like a spin or two, and then oxygen's like, all right, I need that back. I need it. And it goes around oxygen again and again and again and again and again. Okay, you get it. So let's assign charges to this because of what just happened. So the electron is around oxygen much more often than it's around the hydrogens up here. So the oxygen has what charge? Well, it's negative. Okay, they're always going to be negative. So since the electron, which is negative, is around oxygen more, we say that the oxygen is delta or slightly negative. It's not a full negative charge, it's just a partial negative charge because every now and again it goes around hydrogen. If it was around oxygen the whole time, we would say it's full negative, but it's not. So with that, since the hydrogens up here do not have the electron most of the time, they're going to have a slightly positive charge because they don't have that negative charge. Okay? So there's your water example, guys. Water, since the electrons are not shared evenly, they're not shared evenly, right here and right here, okay? These are both polar covalent bonds, okay? So that is a polar covalent bond. All right. That is water, okay? Water is always going to be polar covalent. We also call water a polar molecule. The other example that's a main one, guys, is the methane. And methane has a chemical formula of CH4. So let me draw our carbon in the middle. We're going to have 6 protons. We're going to have 6 neutrons. First energy shell, we got 2. Second energy shell, we have 4. Okay. Let me draw some hydrogens around it. So we have 4 bonding areas. We're going to have a hydrogen here, hydrogen here, one down here, and there's our last one. Let me draw my shared electron in on each one. 1, 2, 3, 4. I'll give you the nuclei too. Here's your nucleus for hydrogen, 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 and hydrogen. Okay, so let me highlight one of these guys here. We'll highlight this one up here, okay, in red. That is hydrogen's electron. Here's what's going to happen. The electronegativities of carbon and hydrogen are extremely close. So this electron is going to go around hydrogen once. It's then going to go around our carbon. And then it's going to go back to hydrogen, back to carbon, back to hydrogen, back to carbon. You guys get what I'm doing here? Okay. It just keeps going back and forth, back and forth. All right. So it is shared evenly. So let me draw our bonds here. We have a bond here, a bond here, a bond here, and a bond here. These bonds, since everything is shared evenly, these are non-polar covalent bonds. Okay. And that makes methane a non-polar molecule. It's like oil and water, guys. Oil and water. Oil is non-polar, and water is polar. So if you put oil and water, they don't combine just because those electrons are shared differently. It's kind of crazy. But those are your two main examples, guys, for nonpolar and polar covalent bonds. And that's pretty much all you have to know about them. Okay. So ionic bonds, guys, we are going to have one electron transferred to the other element, okay? The goal is to get a complete valence shell, and this is what we talked about yesterday. This is when we said, okay, they can gain however many or lose however many. If they are going to want to lose, they're going to give them to an element that wants to gain. And in return for giving an electron, what happens is they get paired together. Okay, so there's a force in between them. Here's a good example here, guys. We have sodium. We already talked about sodium and chlorine. We have sodium that has one valence electron, and then we have chlorine that has 1, 2, 3, 4, 5, 6, 7 valence electrons. What's going to happen here is we already talked about sodium wants to lose that electron. Chlorine wants to gain that electron, so it does. Okay, and you guys can see that red electron on sodium went over here to chlorine. And now both of them have a full outer shell. And since there was that electron transfer, they get a bond between them. Whenever that bond is created, guys, we got, one losing, one gaining. Whatever one is positive at the end is going to be the cation. Whatever one is negative at the end is going to be the anion. So if we go back to this example, a cation is a positively charged ion. So which one is positive out of these two? Okay. The sodium lost an electron, and an electron is negative. So sodium got rid of a negative charge, and you guys can see that's why they have the positive up here. So because it got rid of the negative charge, that leaves it positive. Chlorine gained a negative charge, and that's why it's negative. Okay, we are good here, guys. That's what it looks like whenever they're all bonded together, guys, in almost a lattice structure. Okay, so they kind of make a crystal form, the sodium and the chlorine. Okay, we're almost done for today, guys. So there's other bonds we have to go over. So covalent bonds and ionic bonds are the strongest between the two. We're going to talk about hydrogen bonds a little bit tomorrow. We'll talk about how they gain, or how they are used in order to keep water together. But I think that's enough for you guys today. We went over a lot. Have a good rest of your day.